Thank you, everyone, for having me, and thank you, Marlos, for the kind introduction. It's my first time in Edmonton and visiting University of Alberta and Amy, so really excited to be here. I'm actually new to Canada, so these are some of my first steps of my own adaptation of moving to Vancouver, a little Pacific Northwest. But today I'd like to talk about some next steps in general for vision and learning on how we can have models keep making their own updates, so they can take steps to be more accurate, to be more efficient, and keep doing that even after training. So since this is a talk about updating and adaptation, it's only right that it should tune itself to you. So do ask questions as we go. Let's discuss. I want it to be interactive. Let's get started. So I'm going to be talking mostly about vision today, although the methods could apply to different types of data. So let's begin with why we need learning for vision at all, right? And I'd say the two main reasons are just that the visual world is vast, right? There's a lot of things in it, and it's really varied. It's diverse. And it's hard to totally describe by hand, by our own rules, right? Even things as simple as a chair, they vary a lot in their geometry and their style and their materials, and things like how they're posed or their lighting. So even such a simple object is hard to cover just by our own designs. But if we could collect examples of chairs, and importantly, not chairs, we might learn this difference, right? This learning is not just about chairs, but is essential for all kinds of visual data we might care about, right? Including photos we might take on our own, coming into Edmonton, admiring the river from above, or looking at a local campus you might be familiar with, right? These are both kinds of visual data, but there are other types too, right? Like data we might have from microscopy in the sciences and botany, or data we might have from medical scanners imaging the eye. Different modalities, different sensors, but still visual data, right? Information across space. This is also true of, say, aerial imagery. There's all these different formats and different tasks we might do, in this case, counting caribou. But the point is, all of them have some similarity in their structure, right? They have information across space, they vary in scale. And learning can help us with this whole variety. The same kind of learning approach can be used for all these types of data, right? But in this talk, I want to ask, is learning once just enough, right? Because our data can change. Sometimes it's expected changes, things like the seasons, with winter coming, as I'm sure you're familiar with in Alberta. But also there's more unexpected changes, right? The unfortunate fifth fire season we see in places like BC and California, right? There are unexpected changes that are natural, like fires, and also societal, like in the pandemic, in the response to wear masks and things. Facial recognition systems perhaps were not ready and able to generalize to these new kinds of face images when this first happened, right? So I'd say that while learning, of course, is useful, learning just once might not be enough. So I want to talk about how we can keep learning and have models that can cope with this kind of changing data, since I'd argue we live in a changing world, right? So luckily, though, we have a good point to start from, right? Because of a lot of work over the last 10 plus years, deep learning for vision more or less works. What do I mean by this? I mean when we have nice and neat data like so, at training time, we have this well-posed, well-lit, nicely framed image of a bird, and the desired output, in this case, it's species, a goldfinch. We can learn this problem so that on similar images, we can even recognize this type of bird and others. The trouble is what happens when we go to testing, right? When we deploy this model. The issue is shift happens, The test data can vary in all kinds of ways. We maybe either didn't expect it all or just didn't have the budget to collect and annotate. So this poor little yellow bird might suffer from different kinds of corruptions, right? Things like different noise due to damage to our electronics or our sensors, like Gaussian noise or shot noise. Things like blur, because maybe our platform is moving faster than we intended because it's at full battery charge or we upgraded our drone. Or things like the natural world I mentioned, perhaps weather conditions like snow, or just facts of life and dealing with computers. There can be different amounts of compression. Maybe at training, we had uncompressed images, but then as we kept running our system, we realized we weren't going to be able to store everything. We changed our image formats. It would be nice if our model could keep working. This is not the case for current systems. The issue is not just that shift happens, but it also hurts. If we look at a kind of standard image recognition benchmark, this ImageNet problem, 1,000 different classes, avocados, zucchinis, zebras, what have you. If we look at the error on regular data, the kind of polite data we trained on, we get something like 24%. Maybe that's still too much, but that's the best we can do. Let's consider that good for now, right? If we see even just these corruptions pictured here, this error rate more than doubles, right? Like a catastrophic amount of further error. It's not just because we're looking at this for a ResNet 50, a kind of common model to deploy, but even our biggest and latest models, if you know vision transformers, much larger scale models, have this same pattern. The absolute amount of error is less, but we're still seeing a more than doubling of the error when exposed to these kinds of shifts during the use of the system, during the deployment, during the testing. I'd argue a fundamental reason for this is that while the data can change in so many ways, right, these input X to our model can shift in all these ways, our model itself, those learned parameters, theta, are staying the same. We're applying the same model every time, and we're seeing this kind of failure to generalize. So what I want to ask is there a way to equip our vision systems, or our machine learning models more generally, with a way to adapt themselves on these new shifts? So that when we get a new data, we get a new model as soon as we make a prediction. Because I'd actually argue that shift is the rule. Data keeps changing. In our academic benchmarks, the data stays the same, and this is important for science and comparability and engineering to see what improves. But the world isn't so constrained, right? Because for instance, while I was living in the Bay, we had a day we woke up and the whole world was orange, right? This is perhaps not the time to call a Waymo to get to work. I'm just joking. Great system. If you're ever there, you should try it, right? But this is perhaps not something we thought to put in our simulators or put in our collected data for the training of our models until it happened, right? And it happened in the city. It happened in the countryside. There's a lot of variety here. So what I want to talk about today are what are ways so that as soon as this is observed, our models can change, with, of course, the goal that they change for the better, to generalize more. And to cut to the chase, the kinds of adaptation I'll talk to you about today do, in fact, help, right? So if we look at this catastrophically higher error for both types of models, with types of adaptation methods, we're able to bring that back down. We don't bring it all the way to the happy case of simple data, but to be fair, there's probably some irreducible amount of error here, because it is harder data to work with. If some of our pixels are replaced with noise, then perhaps we can only do so well. So this is to say we've taken some steps, but there are still more steps to take. Yes, question? Great, so the question is, could we maybe prevent some of this degradation by just training more, right? Like, for instance, if I had done some data augmentations, I can add noise to my images. I can change them many ways. Perhaps this could help. These models that I'm talking about were, in fact, trained with augmentation. It's just a question of, can you ever do enough, right? I'm not arguing against learning. If you have the training data, use it. If you have the labels, do it. If you can add more parameters, optimize them. But I think just fundamentally, we can't train on everything because the world keeps turning and more data comes in. So we're going to look at, can we use that data as it is without having to collect a static data set, without having to design more augmentations, without having to pay for labels. Of course, if you have the budget, great, right? But I would say even as our models get larger, because this is what we're seeing here, the VIT model is larger than this ResNet, we still have this issue. Like, it's getting better, but I don't think we'll solve everything in the limit of all training data and computation and model size, because these things aren't free. Great question there, thank you. Right, so a little hint, adaptation can help, but there's more to do. Let's see how we actually get here, though. How are we able to help? We're going to cover today. And the first is what I would call natural shift. So here, think of things like weather, like snow, right? They change the input, but they do so systematically. Even though every snowflake is special and unique, snow as a distribution looks like snow, right? On the other hand, I want to identify adversarial shifts. And here, there are actually changes to the input conditioned on our system, conditioned on our model, to try to cause errors, like an opponent would. It's not clear that each of these shifts will have a distributional similarity that's something systematic like snow would, right? So this is why I want to distinguish natural from adversarial, although they're both ways of inputs changing during the testing. Now, our first question would be, can adaptation learn to help cope with this systematic change, the natural shift? And could adaptation maybe even help learn to defend against attacks, right? The overall view here is for natural shift, the answer is definitely yes. I'm not saying everything always works all the time, but there are many shifts for which we've seen improvement. For the adversarial case, the situation is more complicated. There's some yeses and nos, I think some real questions, but I wanted to give you this orientation to keep in mind as we look through some methods for each case now. Right, let's begin with natural, because these are always going to happen, even if we're in a trusted setting without adversarial errors. So here I want to give a brief tour of ways we might try to do this, right? How we can adapt to changing data by updating when we get this new and different data during the testing, right? Which is, could be to update our parameters, right? Like we were optimizing these parameters in training. Can we somehow keep optimizing them during testing, right? So we'll actually take gradients to get new models as we go. We might also try updating the inputs, right? If it's our inputs that's changing, like we have corruptions, or they're coming from some different part of the data distribution, if we could somehow counteract this, cancel it out, to make our test data look more like the training data, maybe our models don't even have to change. We've solved the problem before we even got to the model. This is another family of approaches. And in addition, there's whole other more exotic ways to update. And we'll see one case if we have multiple models, we can mix them together after their training to change the type of robustness we have and actually continue to make new models from the models we already have. So a non-gradient type of update. Let's begin by looking at how we can update our parameters without any more supervision and without even going back to training. All we have is the model in deployment, and we're going to change this model on the data we see in deployment. And this is also the paper that introduced this setting of what I'm calling test time adaptation. So how can we do this? What we're going to do is we're going to look at entropy, not the entropy of the data of the inputs, but the entropy of our outputs. Right? So if we have a task, like say recognize these images, is it dogs or deer or ships, etc., we can do a quick check and look at on X here, measuring the entropy, so the uncertainty. Right? What do I mean by this? I mean, if we have a corruption of these a prediction of these classes, a high entropy prediction is one that's more uniform, right? There's no single class that's certain. And a low entropy one has more of a peak, right? A lot of the probability is on cat. Now this histogram on the left, what we're looking at is in X, we have entropy normalized to 1. So 0 is the least entropy, and 1 is the most. So going to the right is uncertain. Going to the left is certain. And we've binned it by how much certainty we have to look at the error rate, right? So what are we seeing? Overall, on the whole, when the model is uncertain, it is more often wrong. And when the model is most certain, it is more often correct. To be very clear, this doesn't mean there aren't confident errors. There certainly are. But overall and on the whole, this is the general behavior. And if this is the case, then we might hope that actually the amount of certainty might help us supervise what the model should predict. We could get feedback from the model's own predictions to make better ones. This is, of course, a very well-established idea. There's a paper going all the way back to Granville and Bengio for semi-supervised learning, where we have some data with labels to do supervised learning, some data without to jointly do unsupervised learning. Our insight is this signal alone on purely unsupervised data, data without labels during testing, can still drive improvements. We can make updates from this without needing the supervision along the side to help us. So let's look at this in a little more detail. So now in this plot, every point is actually an entire data set, a data set affected by some of the shifts that I showed you. And the color here is the type, right? So red are noise shifts, blue are blurs. And here we're looking again at entropy on X, and now the true loss on Y, just for the purpose of analysis, right? So there's a few different things going on here. These are all models that aren't adapting, right? We're still just kind of analyzing this role of entropy and all this. And what we're seeing is there's also levels, right? The points that are more filled, it's a little hard to see in the projection, are more corrupted, right? We can add a little noise or a lot of noise. But in general, as we increase the amount of corruption, as things get more severe, we see both the entropy go up, we move to the right, and the true loss is going up. We move upwards. This isn't exactly a line, but they're not unrelated. If we measure the rank correlation, it's 0.6, which is not nothing, right? And so if we were to look at the original test set, it's actually all the way over here, right? So this is data disjoint from training. They're new images, but from the training distribution, right? The same kind of data. This is the least error and the least entropy. If I were to plot training here, it would actually be at exactly the origin, because our models are strong enough that we can fit that data exactly. And 0 cross entropy implies 0 entropy. So the point here is that entropy, at least relatively, can even serve as a measure of shift, right? The more entropy, likely the more our data has changed. But we don't know how much in an absolute sense, right? We can't use this necessarily for accuracy, but it's still giving us some sense that this entropy could have a role in this shifted data and how we might cope with it. So all right, this is analysis. Let's get to an actual update. What's the method? What are we going to do about it? So our update is actually quite small. In brief, we're going to minimize the entropy of our model predictions. We're going to optimize it to be more confident. And we'll do this by updating some statistics that are used inside of our model and updating only a few parameters. We're going to take some gradients, but not too many. And we call this method tent for test entropy normalization. So what do we do? Well, let's zoom in on a particular type of layer. Here we're looking at a normalization layer which is a common type of layer across deep networks. But if you haven't seen it, although we call it normalization, it really has two steps. The first is this normalization of we calculate a mean and variance, right? Statistics of our inputs, so that we can subtract the mean, divide by the variance, try to standardize, right? But having done this, we don't stop. All normalization layers critically include a transformation step, where having standardized, they scale and shift the data. And they do this for each channel, right? Our representations in deep networks are also wide. We have multiple channels. And this kind of transformation is going to happen channel-wise. All the updates of tent are to this type of layer and this layer alone. What we do is, rather than using training means and variances, we can update these live. We can compute means and variances of the test data as we see it. And as we go through our network from input to output, we can use these new statistics so that they're actually a function of the test data. But further, we can also optimize these scales and shifts, this affine transformation. And here's where entropy comes in. Having made a prediction, we'll compute entropy and then take the gradient of these parameters with respect to entropy. Just a single one to update these parameters, to say, try to change the scaling and shifting, all these channel-wise operations, to be more confident. And these updates of both the statistics and the parameters are going to be online. Every time we get a batch, we make a prediction, we make an update. That's to say, we predict, update the normalization going forward. We have our entropy, which we can measure from the predictions alone. We don't need any side channel information. We don't need a human in the loop. We don't need a label. Now we can update the transformation. We have a new model now, right? We have new stats, we have new parameters. We keep this new model for the next batch. And we iterate in this way, right? So every time we get new data, we get a new model. Now, prior work had done these kinds of, you might call them modulations, right? Changing these scaling and shifting. But they learned to do it during training and did it, for instance, from side input. Like maybe you get some text to say, we're going outside today. So now your classifier is an outdoor classifier instead of indoor. Our insight is you can keep adapting these live by optimization as a function of the test data. So you're learning how to do this scale and shift as you go. And furthermore, we can do this during testing because it's actually quite efficient. Like if we look at only these normalization layers, in general, this is less than 1% of model parameters total. So you can do this too, right? You don't need a data center for this. You can do this on a phone or on an edge device. And it can help, right? As a reminder, just in general, updating these stats and these parameters alone are delivering these kinds of reductions in the error, the reductions in the generalization error, even though it's such a small part of the model. It's actually a very effective parameterization. Are there questions on this update or the choice of parameters before we continue? Yes?
Why normalization layers rather than any other parameters or types of things?
Sure, great question. The question was why these parameters, right? There's multiple reasons I can give you. A very simple one is empirically it works. And it works across many shifts reliably. But the other reason is, let's think about our loss here, right? It's entropy, right? It's unsupervised. And there are ways of minimizing entropy that are absolutely not what we want to do. There's degenerate cases. Let's think of one. If I pick a given channel, say it's the channel for cat, I can send this to infinity. I'll get probability 1 of being a cat. Entropy 0. Mission accomplished? Not at all, right? This isn't even dependent on the data anymore. Now, by doing this in normalization layers, as long as we don't do it on the last normalization layer, this kind of degenerate solution isn't as possible, right? Because the standardization will subtract out going too far in any single direction. So part of it is thinking of our loss and where these gradients are coming from. Part of it is, again, indeed empirical. And it's motivated by the computation, right? If we were to take a gradient of every single parameter, then we have to do a full backward pass of every parameter in our network. We would need more memory to do it, and we would need more time. And remember, we're doing this totally online. Like the world might not wait for us to take that gradient, so we may want a faster method. So computational efficiency, empirically what works, and also some thought about what our loss is. Yes?
So I was thinking about this in terms of like, hey, how do we adversarial and from the normalization perspective, can't I just subtract unity, like from the mean of this data? Like I'll make the mean. I'm trying to do this in a way that will shift everything.
Yeah. The means are channel-wise, right? So like the normalization isn't across the different features. So in the case I was talking about where like you're sending a given channel to infinity, that's the output. But all of this is happening in intermediate steps. And so you might be subtracting infinity, but it's infinity for a single channel. You're not interfering with the other channels. They don't suppress each other. Right. So there are more bad solutions than the one that I highlighted. These would be an issue. In particular, we're looking at this method for natural shifts. There are still adversarial things you can do to this, like you just said. For instance, even just giving an image of all black pixels repeatedly could be adversarial for this case, right? But, oh yeah. Yeah. Okay. Oh, why are there any good solutions at all? Kind of, is it? Yeah. Yeah. Why do we find them? Yeah. Okay. Yeah. Thanks for clarifying. Great question. So the question is, why, when doing this kind of unsupervised optimization, right, just minimizing entropy, does anything helpful happen? Because I mentioned one bad case of just send cat to infinity. There's another bad case, which is maybe more directly to your point of, for any predictions, I can always make them sharper, right? If I take all my logits and just multiply by a large number, in the limit, the distribution will converge to a single class. Entropy has gone down, but the posterior mode has not changed, right? Why should this ever change predictions? Why do we see any change in error? This part is key. And so here's where the batches come in. So because we're minimizing entropy across an entire batch, but still for a single choice of parameters, we need a gradient direction, we need an update that actually makes us jointly more confident in the entire batch. And this part is key, yeah. And so I thank you for this question, because that is what's actually letting us find a solution that's better. Because if you did this on a single input, then there are many ways you can make entropy go down that are all trivial and none of them helpful. And this is what helps. Yeah, thank you. Excellent. So, oh, sorry, 1 second. We have a missing slide. Let me fix this. Gonna adapt live for, wanted to show you a few more results, of course, because this is just very high level. Great. So I talked about these overall errors, but let's actually see what's happening for different shifts, right? So this tent method, there we go. At the time it was done, was state of the art for these corruptions in image at C. Of course, I should say was, because further methods have done much better, but they're all descendants of this kind of online optimization, this test type adaptation setting. But what we want to look at here is we're going to compare a source model using the language of domain adaptation. This is just our original trained model, so it doesn't adapt. We'll compare this to just updating the normalization statistics in red, so half of our method in a sense, but also a method in its own right, published at the same time, and tent, where we do the statistics and this entropy update. And gray here is the prior state of the art, which indeed tried to just train harder. They actually tried to learn augmentations adversarially during training to get a model that generalizes more, right? But in the end, they still have a single model, and it's the same model for all test data. So what happens? I actually want to start at the beginning. What happens in the original data? I think for something to be admissible as an adaptation method, nothing should go wrong when the data stays the same. This actually isn't satisfied by all methods. I'll give you a hint. So this is a good sanity check. But okay, what happens when we get to actual shifts? What we see in general is that our adaptive methods, like the normalization intent in red and blue, are helping. They're better than source. And they're even often better than this more sophisticated training method in gray, ANT, for things like compression, for things like weather, for things like blur. They are not doing better on the noise classes, though. I want to highlight this, right? So, sorry, the noise domains. So when we see Gaussian noise or shot noise or impulse noise, this training method is doing better, but actually it trained on them. It was using noises as one of its augmentations. So in the true cases of generalization, we're seeing improvement from our kinds of adaptation methods. So one takeaway from this is that this kind of system adaptation can actually be more robust than train time anticipation, right? Trying to guess what data might happen, because we might not be able to do that. Or another interpretation is there may not be a single model that can actually be jointly good at all these different shifts, right? That's what we're asking for in train time methods. Find me one set of parameters that can do it all. By having these updates, we can actually have a different model of JPEG data, JPEG compressed data, a different model of foggy data, a different model of noise, etc. And so in a way, we're learning more parameters, not by making a larger model, but by making the parameters depend on the data we get. And it's actually helping. Right. So there are other kinds of shifts we might look at. Right? Yes, question. This is totally online, just seeing it once. So one pass. And it isn't keeping any memory of past data. This is just every time we make a prediction, we're also making an update and moving on. That's these 3 steps here. That's the entire thing. So in this experiment, the way that, there's some slide skipping thing. Sorry, a glitch in Google Slides here. When I'm showing these different charts, this is maybe what you're asking. These are all separate experiments in this case, right? For the sake of comparability, we want to see what happens when we adapt to Gaussian noise versus when we adapt to shot noise. But in reality, just different shifts might happen and come one after another, right? A more like continual setting. So people also evaluate this. That's not what's happening in this plot, but that's like a further, more realistic setting. Absolutely, yeah. So good news and bad. If we're doing test time optimization, everything that mattered in train time optimization still matters, right? So the order of the data matters, your hyperparameters for the optimizer matter, et cetera. In practice, for these particular experiments, we've done multiple orderings of the data, and the variance is actually extremely small in the results. That might partly be due to that we're updating such a lower dimensional parameterization in these scales and shifts. So it's kind of constrained in that way. But yeah, in principle, the order could matter. And future work actually inspects that and tries to be more robust to it. Yeah. Great question. Other questions about the setup? Yes.
How far can you take this? I mean, how much further test time adaptation can you do and still keep the original, performance?
Great. Yeah. So here what we're showing is what happens when you process the original data, not what is the accuracy of the original data as you adapt to a shift. So follow-up work to this, in fact, looks at it. And indeed, as you specialize to, say, compressed data, you do get worse at the original uncompressed data. You might think this is bad, but my counter-argument would be, as long as you can readapt to the original data, maybe everything's fine, right? Forgetting could be bad, but another way to look at it is if we have the right model for the data right now, or we can get that right model quickly enough, it could all still work out. But keep that thought. We're going to see an extension of this method that tries to do well on whatever data we see in whatever order, including past data.
Could I just add one thing?
Sure.
So from what I understood from what you said, is that you could adapt to a new domain and then readapt back to your original domain.
Think of the seasons, right? We're about to learn about winter, but then we'll get back to spring and summer and fall. We may have forgotten winter again and need to readapt. But yes. And future work has done this. Yeah, this is the first method for this setting, so it started simpler. But these things like cyclical shift or mixed shifts or a continual series of shifts have now all come with the progress of this topic. Yeah, great questions. Yeah, but yeah, stay tuned. Hold that thought. Yeah, great. So I want to show one more shift and then get back to other ways of adapting. So these corruptions, while some are realistic, were all synthetic, right? They're just things that we did to existing images. Here, I want to look at a different type of shift where we trained on synthetic data, right, like 3D models, and of course, still want to deploy them in the real world. But this is relevant for things like autonomous driving, right, where we can simulate situations we never actually want to cause. So in this case, we're still doing image classification. The metric is error still, so lower is better. And what we can see is that our source model, the one trained only on synthetic data, is quite poor, right, 56% error. When we do tent, with the parameters I told you, these few parameters, we're improving that, but only a little bit. But it may still surprise you we're able to improve it when the images look this different from each other. Yet we can. Now, if we do tent on all, with a little star here, we're able to do better still, right? So the parameterization does matter, and it could be shift dependent, how much you want to update. What I mean by all, this is again, except the last layers. And what I mean by last is the layers after the last normalization. Because if I gave the optimizer access to just the final classifier layer, of course, it can trivially make entropy go down in these ways that we discussed online. So that's no good. But all is all of the previous layers. So this is a more expensive update, but also a more effective update for this more dramatic kind of shift. Question, yes? Yeah. Yeah, so the limits of this are empirical. The question is, like, will really extreme shifts break this? And kind of a problem of all of this is like, shift is where you find it, right? You find out because the model stops working. It's hard to characterize ahead of time. So I will say there are shifts that will break it. And so a reaction and further step of this field is recognizing when has an update actually gone wrong. And for instance, maybe we keep the original model around. so we can reset to it. The first wave is just kind of let's adapt it all, always. And that's part of the reason I'm doing this online, is because even detecting when a shift is happening is itself a difficult research problem. So kind of this is saying just always update. When the data doesn't change on the original one, our error was staying the same because the model actually stays the same. If the means and variances are still the same as the training ones, you get the same model. If entropy is low on the training data, which it is, you don't have a gradient of it, you get the same model. But so, yes, there are cases that fail. So we tried, actually clip art instead. This is a standard benchmark, actually. This often just more doesn't update that much. Like, I think there's not a clear single direction of adaptation. Also, hand-drawn sketches. And the answer is sometimes yes, sometimes no. Yeah, good question about different, there's all kinds of shifts out there. Yeah, so there's definitely more work to be done on when it works, when it doesn't. And of course, for other modalities as well. People using techniques like this. Because the nice thing about entropy, and then we'll continue, is entropy is a function of the output, right? So this could be an image classifier, it could be a sound classifier, it could be a text classifier. People have now done follow-ups to this work across all these modalities, and it actually is still able to help for their equivalent of shifts in their modality. Right, I want to show you one more real-world example. I mentioned Berkeley of, we talked about updating on batches and how we need it. But if we do a task now that's pixel-wise, we make a prediction every pixel, not for every image. An image is like a batch of pixels. So we can even update on a single image, things like semantic segmentation, the prediction of every pixel. So here's an image just from Berkeley during this wildfire that I talked about. So I don't have the ground truth because I wasn't patient enough to label it myself, but we can still look at it qualitatively and you can decide for yourself. So this is an unadapted model, a model trained for this task on city scenes. And I'll tell you, blue is car, and green is tree, and purple is road, right? So there's some things happening here. A number of things are missing, a number of things are in the wrong place. We can first try just updating the statistics, right? And this brings in a lot of the road. We have more of the cars. The trees have kind of gone out of the road back to where they should be. We've even got a traffic sign here, which is relevant to what we should do on a street. If we further do this entropy update, we can still get some further improvements still with more details on signs. I'm not saying we should deploy this in a car right now, but the point is that this can help, although more work is needed. And even just seeing how much change these updates make in the prediction may be a signal on how we curate our data, right? Again, I'm not against training. Maybe we need to retrain the model. But these kind of test time adaptation methods could both help us update in the meantime, but may also provide signals of the kind of data we need to collect from the world the next time we train. So with this, to summarize, the whole kind of point here was we wanted to go from a static model, right, the same parameters for all data, to some process, for instance, by gradients, and these statistic updates that lets us get a new model, a model conditioned on the test data. So now our predictions now are a function of all past data, test data and training data alike, so that we can actually make new and different predictions. So let's go back to our different families of approaches now. We saw one way to do this by updating parameters. There are, of course, more ways, but I showed you a simple way that can work. We could consider updating inputs. And so for this purpose, we've explored using diffusion models, generative models, not just for the purpose of making aesthetically nice images, but generative models to help recognition models, right? Given an image, can we actually corrupt it a little more, but corrupt it in the way that a generative model knows how to process, so we can actually make the model more likely under the training distribution. If we can do that, we're more or less projecting it from some target shift back towards the source distribution, the one that our recognition model knows. So rather than having to train a different generative model of all these different shifts, we can train one generative model of the source data and help it pull data back to that distribution, and actually not update our model for recognition at all. I'm not going to go into that in more detail. I just wanted to highlight it for you as we could try to change the input instead of change the model. And now I want to switch to adversarial shifts to do a quick case study of what happens here. And so remember, this is something where our inputs will change still, but now they're changed specifically to make our model wrong. So to review adversarial attacks and defense in a single slide, which is a very brief scope, the issue here is that if we have an image and our model is working, right, we get a prediction of cat, there exist these small perturbations, these deltas, where I say small based on we have some way to measure them like their norm, below a limit, then we can make our model not just wrong, but very confidently wrong, right? And this is something that is true of many deep networks, almost all of them actually. So people have tried to fix this, but they often fix it by more training, right? Like, can we incorporate these kinds of perturbations into our training to then try to be more robust to them? So this can help, but of course, the attacks might change. We might have to retrain for that kind of attack, and this might take too long. There are other ways people try to do it, like at test time, maybe we add some noise, like augmentation or stochasticity. This can help, but stronger attacks can still break it, because these test time defenses aren't actually specific to the kind of attack that's happening. So most recently, people are trying to use what are adaptive test time defenses. Just like this tent method is changing the model based on the specific inputs, these methods change their defense given that exact input, that perturbed input from an attack. So the question is, do these actually work? So we're going to build up a big table here. But stay with me. We're looking at just a standard evaluation setting for adversarial attacks and looking at a set of, at the time, representative test time adaptive defenses, because people are excited for these new things. And now the exact attacks we use are going to vary, but they're from a standard toolkit. We didn't invent any new attack here. We just tried to apply them as hard and thoroughly as we could. And so what we want to measure is the robust accuracy, right? How accurate are you even in the face of attacks? And there's the results according to the papers, right? Which they're published, so you can imagine they improved. But then there's the results according to our evaluation. And something you'll notice is some are dramatically smaller than claimed. But furthermore, we can be a little more detailed. We can look at what is the robustness using the adaptive defense, but also double check what is the robustness of the base model that this adaptation is wrapped around. Some of these are trying to defend non-robust models that score zeros. Others are based on robust models, right? Like they were trained for robustness. So both trained for robustness and they're trying to adapt for robustness. Does that actually help? We'll look in a little more detail, but we also measure time, right? Because this kind of adaptation isn't free. We have to do something on top. And you'll see some of these are big numbers. So let's actually go through some special cases. All of these explosions there, these are methods that actually hurt. A sophisticated enough attack can point adaptation in the wrong direction. So the method is worse than static, because the update isn't guaranteed in this case. The best method is getting a gain, but it's a gain over no robustness, right? So it hasn't actually improved the state of the art. This is a helpful thing. If you didn't have time to robustly train, great, this helped. But it's not actually pushing out the frontier of our most robust models. And furthermore, a lot of these are actually more than 10 times slower, right? So it's taking us a lot of time to not actually get a lot of advantage. So in summary, none of these adaptive defenses are actually improving over our best static defenses. And all are taking more time, right? So that sounds a bit gloomy. We could ask, like, are adaptive defenses totally defeated? Because 0 of the 9 are better than the state of the art. Half of them actually backfire and are worse, and 2/3 are slower. I'd say it's like dented, but it's not over. We're not done for, right? There's still things we can do. And very briefly, one line of attack can be, again, one line of counterattack could be, could we certify these updates? Is there a way to get a theoretically guaranteed update? We can't do this in general, but indeed, there are ways. And we could also ask, can we change the setting? In this case, these attacks are happening, but on an adversarial training, that's just empirically effective to this. So maybe we need a little more to get a setting that works. Is there something we could adapt with that would actually help? But we need more than just these input images alone. So for certification, I have a collaboration with UBC, with Matthias Lecquier's group, where we are able to derive an adaptive form of randomized smoothing, which is guaranteed to not hurt and can only help in this adversarial case for a specific type of update, but still a test time update. And now for changing the setting, there's also something we can do here that I want to show you briefly, where we're going to need a little supervision. So like a few shot number of labels. But with these labels, we're going to be able to specialize our robustness, even after training, to do better. So while these adaptive defenses failed because they're purely unsupervised, maybe other characteristics, there are other settings where we can help. So right, if we go back to our families of methods, I wanted to highlight our only theoretically sound project in the whole talk, just to be very clear about what's empirical, what's theoretical. This adaptive randomized smoothing one is theoretically sound. That's one way to update if we're happy to do some math and prepare ahead of time to do it. Now, this other case of mixing, we're going to look at actually merging different trainings. And here are the different experiments. Maybe we could even merge these trainings across Canada. Take an Alberta model and a BC model and merge them in the future. But first, we're going to look at what we mixed for robustness. So when I talk about mixing models and combining them, I want to orient us to what kind of combination we're going to do. So you may have seen ensembles, right? So our ensembles use multiple models and combine their outputs. So if we take this nice image of Ottawa, if we have 4 different models, we can run it through each. We'll get an output for each. And now we can combine, say with some linear combination, right? We have each output and we have a weight for it. And perhaps this can help on its own, right? But it costs us something to do it. Now soups, if you haven't seen them, are also a way to combine, but perhaps surprising. Here, we also have multiple models where we're going to mix not their outputs, but their parameters. We're going to mix all the parameters together, meaning the architectures have to be the same for this operation to even be defined. But if we have a parameter and a weighting, we can mix all these together into a single model with the mixture of their parameters as the effective weights. This might sound totally insane, and it should. There are cases when it can work, and we're going to talk a little about it, but just stay with me for this slide. It's a linear combination of these nonlinear model parameters, yes, but it's in parallel, right? So like the first layer is the mix of the first layers. The last layer is the mix of the last. But the point here is now we can put our input in, we get an output. If we think about this computationally, right? So linear combination of output for ensembles, linear combination of parameters for soups. How much work do we have to do to make a prediction? For the ensemble, m models means m forward passes, right? M times we run a model. For the soup, how much work do we have to do? If I have m models, so it's just one, right? Because we're always mixing down to a single model. This starts to sound attractive for test time, right? Because we can have multiple models, but do no more work for our inference. But the question is, where do these models come from? Where do our thetas come from? And how do we pick these weights W? And also, how could this work at all, you might ask. So let's get into it. So in our project, which we call seasoning soups, because it's a follow-up to this original soups paper that discovered you can do this at all, we're going to make our ingredients, our model parameters, by doing different kinds of fine-tunings for robustness, right? So we can do trainings with types of attacks limited by different norms. What are these going to be? So the trick is we're going to start from one single model. We're going to start from a model, our model 0, trained with adversarial attacks to this L infinity norm. And all the other models are going to be fine-tunings from it. Fine-tuning without attacks, fine-tuning with different attacks. And this fine-tuning property is what actually allows us to do this mixing. So all these models are related because they have a common initialization. And while they're different, if you fine-tune enough, but not too much, you can have this mixing and have things help. That's the very shorthand way version of how soups are possible. So these are our ingredients. The other thing we need are the combination weights, right? We need the W's to make a soup. So here, this is where the supervision is going to come in. With a small few-shot data set, but from a shift or from a type of attack, we're going to use this to pick W. And we'll do this very simply. You can do this by random search or grid search. You just take a W, we can instantiate theta soup and run it, right? So this only requires inference. It requires no gradients, right? We just make a model, score it for how well it does, choose it, the end. So this isn't test time adaptation in the same way I told you about with no labels, but it's still a kind of test time or post-training update, right? We need labels. We need this kind of pre-training to have multiple models, but we don't need any retraining. No further gradients are taken during testing. We're just remixing these W's. Yes? So there's a trick, yeah. So all of the models, except for 0, are initialized from 0. This is the relationship among them. So they all share the common parameterization of the first training. If you just did 4 trainings in parallel from scratch, these are absolutely not mixable, and there's no reason they should be. Yeah. So it's this fine-tuning relationship that's key. There's still some murk there, but that would take a talk of its own. I'd be happy to talk about it offline though. Yeah. It's a fascinating topic. I'm still working on more types of soup. But here we're looking at these different types of robust fine-tuning to go into our soup. Yeah. Okay, so we can pick these W's? Yes?
A more naive question. The
Please.
theta soup
Yeah.
is what's actually used with one network. So when you say 4 passes, it's just a 4 pass of one network.
Yeah, that's right. Great question. The question is, for this theta soup, like, how do we actually use this now, right? Because we have multiple parameters going in with their different W's. This equation is showing us getting a single theta soup, but where does it go? All these architectures are identical. It's like the same model, like a Resident 50 or a VIT or whatever, what have you, LSTM, don't care. Once we make this mix, we're going to use that in our single instance of the network. Yeah, and that's what's making the prediction. Yeah, great question. Thanks. Yes.
Is the soup constructed over, like, each theta is per layer or per weight or per network?
It's just network. Like the W's here are scalars. W0 is a single number, and W1 is a single number. This is what I meant by it's mixing across the layers in the same way. You could do more, but this is enough. Yes, question, great, yeah. Yep.
Is it like a convex combination, or the weights can be positive and negative?
Keep that thought. I'm going to show you, yeah. In the original soups, it was convex. And even just the average, just simply 1 over m was enough to get interesting effects. But the point is, we're now going to pick these W's, right? We can think of where does the distribution of W's come from. So let's see. So first, I just want to look at convex combinations, where now the corners each are a different robustly trained model, right? And this is now looking at robustness, different types of adversarial attack. Either these single types of norms, like blue is L infinity. If you don't know the different types of norms, just think of it as different types of attacks that could happen. This last black one, though, is actually a mixture of attacks. Because why should an attacker be polite and only use the type of attack you train for, right? And the point here is the corners are the specialized to a single adversarial attack models. Every intermediate point is a mix. And what's interesting is so the saturation of the color is how robust we are. Sometimes the most robust model is in the interior. It's not always picking a corner. So even if you train for L2, you can actually get better robustness by using a mix of an L2 and an L1 and L infinity model. In some cases, the best is the expert, like L1, you should just use L1. But the point is, this is not always the case. So here the combination is convex, and we're still looking at only adversarial shifts. But let's generalize, right? Let's free our minds. Let's think about other shifts. So here, in this bar chart, every column is a different type of shift. ImageNet C are those corruptions I showed you before. Sketches are hand-drawn sketches, like was asked about. R includes things like paintings and even sculptures and things, right? So different kinds of shift. And now the bars here are which ingredient do we use? Which model is in the mix? And what I want to point out, based on your question, was the range of W here is now actually going negative and higher than 1. So we left convex combinations behind. Want to just look at linear combinations. And in fact, we can see the best soup selected for certain models includes negative components. So this model is actually less like this pre-trained model. Which one is it? This is nominal. This is training without attacks. So let's talk about this shift. Conflict stimuli is a benchmark where the texture, right, like a shirt or like carpet or whatnot, disagrees with the shape. So you have a cat made of metal, like a car, or you have a car made of fur. The true class is the shape. Existing work has shown that many deep networks are biased towards texture when you do standard training. So for this shift, we're seeing that pop out, where it's actually subtracting out that behavior of preferred texture when you're being scored on shape instead. So takeaway here is actually the composition, the mixing of the soups does depend on the test set, right? And we're seeing this kind of adaptation where we're picking different soups based on the few shot supervision we're getting. Now this is a big table. Don't worry about all the numbers. I'm going to take you on a guided tour. These are all those same shifts, but now looking at many baselines that either do more training, right? Like let's train harder, like people asked, or they're using multiple networks, like the ensemble, right? This 4x means 4 models actually get to run some more computation. Let's just look at the mean, because there's a lot of columns here, right? This is the mean over all the shifts. And now we can consider how much does just one single soup for all shifts help us, right? This is this line here. We're actually doing competitively, but not necessarily strictly better than the previous methods, right? But this is with that constraint of we have the same model for everything. But let's go a little further. If we mix a soup for each shift with that little bit of few shot supervision, now in the mean, we're actually doing better than any previous approach, right? This is possible because the soups are so quick to mix, right? It's only this linear combination of the parameters. We can do that instantly. Not quite instantly, because there's the time to check if that was a good mix by doing validation. But still, there's no gradient optimization. It's just, let's score it. We can pick it. So this is, again, seeing a way that we can do updates to do even better, because that update can be more specific to the data we have right now. So with that, I would like to call attention to the original model soups paper, because it is quite fascinating. This soups paper from Wartzman et al. At ICL 22. This work was our extension, where we looked at soups of robust models, because people didn't know you could combine models across types of adversarial training, and with this further exploration of how do we pick those weights, W. Here, the soup is actually P soup, or maybe even LP soup, if you like adversarial norms. With that, I do want to make this transition from test time updates of a single model over time, right? With tent, we saw that we could go with our xt, we'd have a model at time t. The next batch, we'd get the next model, right? I want to instead think about, are there ways we can use multiple models at the same time? Yes, a question. Right, okay. Yeah, let's briefly cover that. So I looked at these common combinations. You can try to do joint adversarial training across all the attacks, but often the model ends up specializing to one of the attacks because maybe the loss is lower for that single one. So it's hard to actually do this in practice, to just make something trained to all things at a time. So this is another reason to perhaps be able to select them. But I'd be happy to go in more detail offline about that. Yes, question. How do people do against these adversarial perturbations? Yeah, they're basically imperceptible to people. Like at the size of the change that's being made, they're not adversarial to humans at all. For fun, people have tried to make image transformations that make humans wrong instead of deep networks. This can also be done. I know less about it though, to be honest. But if you're curious about, yeah, for the kinds of adversarial shifts we're talking about, they're not like the things I showed you, like snow, where even you'd have a harder time doing it. Like it's trivial for you to know that it's still a cat, but the networks are all convinced it's a zucchini. Yeah. Great clarification question. Yeah, these are small perturbations in terms of human perception, but they're big. Oh yeah, sorry. Oh yeah. So these shifts, human performance is different, but it's still not hard for people. Yeah, like you can recognize a sculpture of a cat versus a dog. A network is less good, or you can recognize a cat made of metal still. But yeah, you're right. There is, for some of these, an element of just the task is harder. But that's a smaller effect than what we're seeing in the sensitivity of our models. Yeah, good clarification. Okay, I do want to tell you about this last thing, because this is, I think, the frontier of the field, and where I might convince you to join in the time we have. So right, one way to look at this adaptation or continual learning is that we're getting a sequence of models for a sequence of data. But now I want to do a very quick tour of, are there actually ways to use more than one model at a time? Maybe this sounds like more models, more problems, but actually we're going to see how it can help us in a few ways, right? So here, I mean, we might have complementary models, or given an X, we can choose among different models, or maybe some set of them, to try to do our work better. So in the first one, I want to stay with this setting of test time adaptation, right? So I showed you few shot labels and soups. We're going back to unsupervised now. All we get is the test data. Let's try to deal with it. But now, what we're going to look at is, can adapting a single model actually be enough, right? If we keep seeing more and more and more data, it could happen that our adaptation starts to drift, and actually the error goes up, right? Because we don't have labels to help us. We're just trying to do our best as we can. We're not guaranteed to improve. We could do something like regularize our updates, seen in this solid orange line, right, where the error isn't going up, but it's also not really going down much, because now we're saying adapt, but don't adapt too much. What we'd like is something like this blue line, where we can actually keep adapting, we get better the first time we see a shift, and then we stay okay if we see the shift again. So this is that cyclic case, right? Like winter, spring, summer, and fall keep coming around. A further thing we might want is, if we keep seeing a shift, like winter coming every year, well, if we can readapt fast enough, maybe it's okay, right? But what about that first day of winter? We don't want all the cars to crash, or we don't want all of our facial recognition systems to be confused about people, right? So an existing method, it does in fact keep readapting. This is good, right? When we see a shift, the loss goes down. But first, the loss always does spike, right, when that shift begins. The dotted lines here are the boundaries of seeing the shift again. Now here in blue is our new method, where what we would like is the number of times we've seen a shift, we should be better and better at it, ideally. We want those spikes to go down, and that's what we're seeing. It's not perfect. Again, it's still unsupervised. But the point is, when we cycle back to a shift, we can be better at it. How are we achieving this? Oh, sorry. But we have a method that can do this, and it's doing it by actually clustering the data as we go. And every time it makes a cluster, it actually makes a new model, but totally at test time. So if you know mixture of experts, this is a completely test time and unsupervised mixture of experts. But these clusters aren't necessarily perfect, right? They're just inferred. So here, the colors are the true domains, the true shifts. Things like the noise I showed you, things like the blur I showed you. But now the numbers are the inferred clusters. And you see, for instance, we've combined Gaussian and shot noise into a single cluster. But actually, this does better. In a way, it's pooled the data together to make more updates on this inferred combined domain. Or you can see also that this one shift of contrast has actually received two clusters, 10 and 11. It turns out these are the low contrast images and the high contrast images, which the model decided to cluster differently. So this is a way where we have more models, but it's actually helping us because since we have a model per cluster, the model for the old data can stay there and remain. When the data comes back, if we're able to route back to that cluster, we've in effect remembered it instead of having to readapt. Right, so we're not only updating the model, but we're splitting and merging these models. So just like we saw soups, we actually, when we get a new batch, we pick a set of models to use, soup them, because these are all updates of the same original task model. One trained model went into this process, multiple test models come out. And we found we're able to also recombine them in this way. So even though we have multiple models, we're not paying for all of them. This method only takes like 2x the amount of memory, even if we have 100 different models, because they share a lot of parameters, and only about 1.3x the time, even if we have 10, 20, 100 models, because of this routing. So this is where coming out at this NeurIPS. So you're right up to the last step of what's going on. I see some questions. I just want to finish the tour of a few other things since we're near time, but I'd love to chat at the end. Further, so now we're going to go to train time. This is not a test time adaptive method, but still a way for models to help each other. So in deep learning, generally, we've seen bigger is better, right? In this case, x-axis is size and the total amount of computation, and y-axis is different kinds of accuracies across tasks, right? And we see, and the size of the dot is the number of parameters. So as models get bigger, they're getting better. But what if we need to get up here? We're not quite good enough. You could define a bigger model, but guess what? Now it's your job to train it. And that's a lot of work. So in this project, we actually want to see, can a small model, can we take one of these dots and use it with one of the bigger dots and actually get something better, right? Because these models exist. We could take them from the models that were pre-trained models. So if you think about just a single model as our 1x compute, we're going to look at combining models of different sizes. We're going to fine-tune them separately and just only learn how to combine them. And compare this to things like ensembles, right? Where the ensemble takes just linear, like integer multiples more, right? M. Instead, think like 1.1x and 1.2x instead of 2x or 10x. We do this by separate experiments. You don't have to train these jointly. So you're probably using the largest model you can already afford. So doing this jointly probably doesn't work. In this method, you don't have to. No joint training, like I said. No requirement in architecture. You can pair a giant VIT and a small ResNet, or a big shuffle net, or whatever you want. And the excess is think 10% more computation, or 20% more, not 100% more. Remarkably, this can actually help a lot across various things like accuracy and uncertainty. So each of these little points, this is what we call a duo, a pairing of a large and small model. The blue is where you just combine them. You just average. You don't learn the average. And sometimes it helps, sometimes it hurts a lot, though. You see a lot of blue below the line. The red line is just use your biggest model you can. But orange is actually quite reliably, not always, but quite reliably above. So the small model, even though it's worse than the big model, when combined with the learned weighting, is actually helping and not dragging down the big model. And it's not clear that has to happen that way, right? This is true of accuracy. It's also true of different measures of uncertainty. So this can give us more robustness about knowing when the model is right and if the model knows it's right or not. And last, I want to talk about not just robustness and uncertainty, but efficiency. Are there ways to use multiple models to actually get a faster system? And so here, what we're going to do is try to learn not just what to see, what's our representation of an image, but we're going to try to learn where to look. And we'll do this by taking our biggest and deepest and best self-supervised models, models that have learned without labels, and seeing where do they process. So like in this image of a building, it's looking at the building and not the sky. Or in this image of birds in a tree, it's looking at the birds and not all of the tree. By looking, I mean, where does it attend to? We can measure this as the attention in the model. And what we're going to do is rather than do this big, deep computation, because it's expensive, we're going to learn to predict it with a shallow computation, right? So that if, for instance, we want to recognize this bird, we can give our big model only the relevant about what should we actually extract as a representation. But we can learn these both in parallel from one single teacher. And notice these are just gradients. This is just normal deep learning optimization. There's no tricky approximation. There's no reinforcement learning. Maybe you could do even better. I would like to use reinforcement learning, but sometimes when you try, you think, I know, I'll use RL. And now you have two problems, right? You need to make RL work and learning to work. You could probably do better. My point is this is a very simple optimization compared to RL, and it can work for us, right? If we look at efficiency and speed, so throughput, higher is better, and accuracy, we're out here on the frontier. And sometimes even just as accurate as our big giant teacher model, but strictly faster, because we've learned to approximate it very quickly by factoring out our responsibilities, right? The selector model figures out where, and only condition on that where does our big extractor model work out the what. So actually more models working together can be faster if we design them to work together in this way. So with that, I'd like to say, it's your chance to step up. I want to work in a world where we keep learning and adapting while our world keeps turning. So we get a future of more models, not fewer giant models that only certain institutions can actually afford to make. Right? These kind of test time updates I talked about are things you can do at large scale and small, at different kinds of platforms. So we could all give it a try. And in general, I see this as a kind of way, one step you could take along the way is check out our latest workshop. The second workshop ever on test time adaptation was held at ICML this summer, and all the materials are online if you want to learn more. Or you can ask me. But the way I see this in general is this kind of adaptation, this adaptive computation, is moving us towards a kind of more evergreen workflow of machine learning. Rather than having to start and stop things when we realize they're wrong, our models can always be trying to update and learn and improve, whether that's improving accuracy or even potentially improving their efficiency. Can they learn how much to compute as they go? Or to put it more academically, it's a way to keep our models in school and studying. Or like we say at UBC in our motto, it's your turn. So it's the model's turn to work now. With that, I'd like to conclude and say thank you. And here we go. Yep, thank you to you, and thank you to all my test time adaptation crew. Thanks.